In the machine learning course project, we choose a paper from CVRP 2017 to reproduce and improve. The group members are Dongpu Luo, Qilong Yun, and Kongwen Kit. This paper presents PointNet, a deep learning technique for analyzing 3D data. PointNet extracts for an important feature from point cloud, which closely resemble the original sensor data. Prior to PointNet, researchers encountered challenges when applying machine learning models directly to point cloud. They have to convert point cloud into different data structure to effectively use this model. However, PointNet provides a unified learning framework for applying machine learning to 3D point data groups, including tasks like object classification, part segmentation, and semantic scene phrasing. PointNet addressed the challenge of handling unordered point data group by developing a neural network that is irrelevant to the order of points in point cloud. The researchers utilized the metric functions within the neural network to ensure consistent outcomes regardless of the input ranking order. They employ a multi-layer perception network to project raw data points into high-dimensional embedding space, and use max pooling to aggregate point embedding using the symmetric functions. PointNet also ensures geometric information invariance for point cloud inputs so that it can maintain consistent representation for 3D data group despite rotation. It achieves alignment with a standardized cloud space through an affine transformation using TNet. The researchers also introduced regulation laws that enforce proximity between the transformation matrix and orthogonality. PointNet's architectural design is very concise and very efficient. It uses TNet to transform the input of point cloud of endpoints represented by XYZ coordinates. Each point is then embedded using a multi-layer perception, resulting in a 64-dimensional embedding space. A feature transformer further transforms each point into a distinct 1024-dimensional embedding space. To obtain a comprehensive representation, max pooling is applied to aggregate all points in high-dimensional embedding space, generating a global feature vector. And this vector is the basis for generating K-score for classifying K candidate categories. The local embedding and global features vector are concatenated for segmentation tasks to predict class score for each point. The results are obtained by evaluating the classification datasets. In PointNet, the datasets undergo sampling and transformation in the processing stage, a shared MLP process each 3D point, generating a 1024-dimensional representing vector. However, max pooling failed to capture important local features and interdependency information. To address this, we integrated local features from 3D data points into the representation vector. Inspired by CNNs, we adopted PointNet++, which introduced the set abstraction process. This includes a sampling layer, a grouping layer, and an MLP with a max pooling layer. Techniques like fast point sampling and ball query are used in set abstraction to define local region and extract local features. Its operation can be stacked for increasingly abstract local features. To consolidate local features, so PointNet++ introduced the MRG strategy, which group features from the set abstraction stack. This stack combines the local information from different dataset levels. So in our study, we modified the PointNet classifier architecture by replacing a layer with 3 set abstraction blocks. Each layer samples a subpoint set and combines the local feature using MRG. This modification improves classification accuracy and reduces computational costs by reducing the number of 3D points through set abstraction block implementation. We conduct experiments using the PointNet classifier, sampling 1,250 out of 2,048 3D points for training. 2 models were trained with random sampling and the forest point sampling, FPS. After training for 40 epochs on the ModelNet 40 dataset, The models were evaluated using the EPIC 39 model for the test set. FPS achieves slightly higher classification accuracy, particularly with fewer sample points. Furthermore, we developed a modified model that is incorporate local features through the bioquery process within the set attraction block. Classification accuracy are present in the table demonstrating our experimental result. Comparing with the sample method, FPS showed slight increase in the prediction accuracy. Moreover, our model outperformed in the original point net even with the random sampling. It showed lower sensitivity to decrease the number of sample points, highlighting the importance of multi-level local features in distinguish different datasets. So, in conclusion, incorporating multi-level local features significantly enhanced the PointNet classifier performance in accurately classifying point clouds, regardless of the sampling method employed. By the way, we have an additional idea that is currently lacks of implementation in code, and the video length is only 6 minutes, so we don't have enough time, and we wrote our idea in our report, so please read it if you can. Okay, so that is all of our presentation, and thanks a lot for listening.